Hello and welcome again to the continuation of our first lesson on Chapter 3, Fitting Functions to Data. So, on the previous lecture, I have told you, or I have taught some of the basic terms in linear regression. And one of the important terms in linear regression is about the spreading of the data. And when you have a spreading of the data, sometimes you couldn't fit all the lines, so that the solution that is being used by mathematicians in modeling this spread data is through the computation or solving of a regression line. Now, a regression line is the best fitting linear function. Okay? When you say best fitting, it is a line which, in the layman's term, it is the line which closely fits all of the given points, or are very close to the given points. Now, this is our data. Okay, this is taken from the example on the previous lecture, and we have our days and sit-ups. This is taken from somebody who got injured, and then upon taking note that he or she is recovering from her or his injury, now he decided or she decided to have a test on the sit-ups. So these are the data for the days that this guy had according to recording, and this is the number of sit-ups that for each day was he or she be able to complete. Now, when we plot it, I use Excel for plotting the table. So in Excel, all you need to do is to encode this table here, or this list of data, okay, and then press on the graph. There is this symbol for graph, and then automatically when you highlight these two data here, there will appear a linear line, or a graphing which will look like this. Now it depends. You have the Microsoft Excel with you, you can try doing this one, okay? But the only available, I think, design is like this. So we have these points which are actually diamonds or inverted squares, rhombus in other words. So anyway, this is our data plots, okay? And from here, we are going to introduce you again for the second time to linear regression. Now, according to solving of these points here, we could get a mathematical pattern or mathematical equation for this entire data by the use of a regression line. And the regression line, of course, the first requirement is you must have a graphing calculator, okay, a grapher. This will ease your computations for linear regression or regression lines, okay, because your calculator is capable of computing the equation for regression line. All you need to do is to enter the x and y values into two lists on your grapher, and then from the statistics menu, there is a statistics menu there. Just run a regression line in the form of y hat. So just run a regression line in the form of y hat is equal to ax plus b, okay? And then it will give you the best fitting linear function, which in this case is y hat is equal to 2.1x plus 3.4. Okay? Now, how did the grapher do that? Well, first, he assumed a best fit line which run through this point. Okay? And of course, when you run a line through that point, this is according to your grapher, of course, okay? It will somehow trespass those other points. So notice that the other points are not located, or they are not located on the line, okay? So most of them are outside the line. They are either below the line, or above the line, okay? Now when you draw a certain, when you take the mean of this line, okay, it will somehow appear like this. So what I did here is that we have the original lines. The original lines are here. It's too big. So the original lines are here, here. I mean the original points. I'm sorry. Okay, original points are either below or above the best fit line. So it's here. Now you can draw another other points, okay, such that these points will be above, either above or below those lines. So notice, okay? And we are being introduced to a new term here called the residual. Well, the residual is just the difference between, what do you call this? It's the difference between your original y value and your uh, y hat. Okay, so this, in this case, the residual is this. Okay, now so much for the introduction. So now we are going to solve a problem in 3-1, which will actually engage you and make you more confident in solving regression lines. Okay, so this is taken from page 129 of your book Pre-Calculus by Forster. Okay, so we are on exploratory problem set 3-1. So the first question, the first problem there is enter the x and y values in two lists on your grapher. So you get your grapher, enter the x and y values in two lists. Okay, so for x values we have these values 2, 4, 6, 8, and 10. And for the y values, we have 8, 10, 19, 18, and 25. Okay, then from the statistics menu, run a linear regression in the form of y hat is equal to ax plus b. Now, upon doing this, you would be somewhat amazed that the resulting equation is actually y is equal to, or y hat is equal to 2.1x plus 3.4. The y hat, as I've said, is the best fitting regression line equation. Okay? Number 2, plot the given points and the linear equation from problem 1 on the same screen. Does the result agree with figure 8-1b or that figure? Okay, the figure for this. Okay, does it agree with this? Now let's take this one onto the next slide. So let's take it here. This is the graph of the linear, or the this one. Okay, this is the graph of this tabular data here. So we are going to test if the same holds true for this given equation. So of course we're going to find the values of x and of y according to the given values of x. So by table alone, you know, you could already know that they could confirm to each other. So in other words, what I'm trying to do here is to simplify a bit of finding or confirmation. I am going to plot or I am going to find all of the points, given these points also that uh, given these points for x. So the points for x are 2, 4, 6, 8, 10. So let's use those points to find for our y. Okay, so I am actually writing my x and y values. So this is for my x, and this is for my y, and my x is from 2, 4, 6, 8, 10. Now according to this linear regression equation, okay, so if my x is 2, then that's 2.1 times 2 plus 3.4, and that will give me 7.6. Okay, so 7.6. And then when I have x as 4, then that will give me 11.8. Okay, if my x is 6, then my y is 16. If my x is 8, then my y is 20.2. Okay, and if my x is 10, then the value of my y is 24.4. Now notice that they are very close to the values taken from the sit-ups. So if if your x is 2, then your y is 8. But in this case, so let's compare them side by side, okay? So we have 2, 7.6, and here 2, 8. So almost close. Well, for 11.8, so a little bit off, but still close. We have 6, 16. This is 3 units away from this. And then for 8, it's 20.2, 10, 24.4, using this equation of the regression line. Okay, so let us plot all of these points for the one given in here with this. So if my x is 2, it's 7.6. So it's approximately here, right? If it's 4, to 11.8. 4, 11.8. It's somewhere here. If it's 6, it's 16. So 6, 16, it's here, right? Okay. If it's 8, it's 20.2. So 8, 20.2, it's somewhere here. And then we have 10, 24.4, so it's here. Okay, and then running a line through these points. So this is what it looks like. Okay, and you can see that they are similar. So the results agree with the figure that we took from uh, the previous figure. So you can see they are similar. I'll put it here. So they are similar. Okay? Do you understand? I mean, is this clear, right? So running the linear regression, okay, makes you have, the same graph actually from the graph when you plot all of these points, okay, are the same with this. So we got the same graph as this one, right? Okay. For number 3, show how to use the linear function to predict the number of sit-ups Mo could do 2 weeks after surgery. And what real-world reasons could explain why the actual number of sit-ups might be different from the predicted number? So first, 2 weeks means like 14 days, right? So we have to compute for f of 14. And we are going to use the regression line when our x is equal to 14. That means we have 2.1 times 14 plus 3.4. And this will give us 2.1 times 14 is equal to 29.4 plus 3.4. This will give us 32.8, or this is approximately 33 sit-ups. Okay, so after 14 days or 2 weeks, then Mo could do at least or at most 33 sit-ups using this linear regression equation. So what real-world reasons could explain why the actual number of sit-ups might be different from the predicted number? Well, we could predict that, after 2 days, so 10, 12, this would be around, what do you call this, like 27, 29, something like that. But we couldn't really predict, okay? I mean, we could predict, but sometimes it could be out of proportion. From the given table, what I'm trying to say is that our prediction could be true or it could not be true because, as you know, 14 days or 2 weeks is outside of our range, right? So it's because outside of this given range from 2 to 10 makes us extrapolate certain values for our y. And sometimes, or most of the times, that gives an incorrect prediction. So therefore, when you extrapolate or take values of x which are outside the range of the given table, then it normally gives an incorrect prediction. That's why in the real sense of the word, okay, then the actual number of sit-ups might be different from the predicted number. So that makes sense, right?